So, hi everyone. Let me introduce myself. First of all, you can call me Cedoor, and you can find me on GitHub, Telegram, and Discord with this username. So, what I would like to do today is not only to provide an understanding of what Semaphore is, but also to show you more details about the implementation and our vision for the future. Trying to outline like a path that meets the needs of developers, but also end users. So I will start with a brief description of Semaphore. Then I will talk about the evolution of the protocol very briefly. Then I will talk about the core principles, but like from a software engineer's point of view, so not high-level principles. And I will talk about like the main technical concepts behind the protocol, and then Semaphore v4, which is like the next version. And I would like to explain to you what Semaphore v4 is, what we have like worked on, and maybe ask you like feedback too. So yeah, let's start with a short definition. Semaphore is a zero-knowledge protocol, and it allows you to prove that you are part of a group. So it allows you to join a group, first of all, and then it allows you to prove that you are part of that group anonymously. So it's an anonymous proof of membership. And in addition, you can also send signals like text messages, votes, or feedback anonymously. It also provides a simple mechanism to prevent double signaling or double voting in case you are building like a voting application. I will talk about it later. So Semaphore is a public good, so it's free and open source. You can like read the code and you can contribute. Let's start with a simple example in order to understand how you can use Semaphore. Witness protection. There are many examples we make usually, like voting applications, feedback applications, but there are also like other examples like this, which are very useful in my opinion. And according to the Corruption Perception Index, most countries in the world still have a lot of corruption problems, as you can see here. So in this case, Semaphore can be used to allow witnesses of crimes or corruption to anonymously submit evidence or testimony. Yeah, this is just an example in order to understand what you can do with Semaphore, but there are many, many use cases because since Semaphore is like very general purpose. So let's talk about the evolution of Semaphore. So the first commit on GitHub is dated at May 2019, so it's 4 years ago. And in February 2020, Barry Whitehat, Wei Ji, and Kobi Gurkhan published the white paper of the first version, and the first version was released. So circuits were a little bit different. They were more complex, but the main concepts were the same. So identity, groups, and signals. Then Semaphore v2 was released in June 2022. The protocol, everything basically, libraries, circuits, and contracts were made like simpler. And Semaphore v3 was released in January 2023. So more JavaScript libraries were added, and the focus was mainly on developer experience and documentation. Finally, Semaphore v4, we have worked on Semaphore v4 lately, and we hope to release it like in the next months. And we hope to collect feedback here at this event in order to make it even like better. So let me spend some words for the core principles that has guided us to date. They are like, I'm a software engineer, so they are like from a software engineer's point of view. But there are, of course, other high-level principles which are very important, maybe even more important than this, but this is still important. The first one is accessibility. So good documentation, self-explanatory code, and simplicity. I think this is one of the most important ones. We have tried to work on that with Semaphore v3, and we have tried and we will try to work on that with the next versions too. I feel like A lot of zero knowledge protocols are not really easy to understand, as you know, so we are trying to make Semaphore super easy, not only for people with like a zero knowledge background, but even for people without any zero knowledge background, even web developers or even like people who don't have any background, like programming background. So the second one is composability. Composability is an important concept inside the Ethereum community. The whole ecosystem has been built with this concept in mind, in my opinion, and it's very important to give more importance to this concept aspect when we build zero knowledge protocols too. The third one is efficiency. Making the Semaphore packages more efficient and light has been one of our main goals lately. Zupass, as you may know, uses Semaphore, and we have been like able to make proof generation verification much more efficient as soon as we have noticed like some weaknesses while using and building Zupass itself. And that made me realize that we can actually understand what we can improve in Semaphore only when Semaphore is actually used by real people, like Zupass. So yeah, hopefully in the future we will make it even more efficient. So I will start talking about the main concepts, the main technical concepts in Semaphore. The first one is identities. As you can see, there is like a JavaScript library you can use to create identities. It's pretty simple. You can create an identity in 3 different ways, randomly, the first line of code without any parameter. The second one is like you can create a deterministic identity with a secret message. And with the third way is importing like a Semaphore identity from a previous created identity. A Semaphore identity is made of like 3 values, 2 secret values, the trapdoor and the nullifier, and 1 public value, the commitment. The secret values are like your private key, basically, whereas the commitment is your public key. So what's happening under the hood? Basically, we are using SHA-256 to hash the secret message. Then the message is split into 2 parts and assigned to each identity secrets, 1 for the trapdoor, 1 for the nullifier. Then we use Poseidon to hash the secret, and we hash that secret again. So yeah, this is a little bit tricky, and we have tried to make it simpler with Semaphore before, for example. The second important concept is groups. Is about groups. Groups can be thought as anonymity sets. Groups are very important, not only like from a technical point of view, but in our society too. Groups are very important. So they are a way to establish necessary trust among participants. As you can see, there is a library for creating groups too. It's pretty simple. And what are groups? Groups are actually Merkle trees. So we are using Merkle trees because they are a very cool way to prove that you are part of a list of like members, in this case, of a list of identity commitments, just sharing a small portion of the tree. So we can even use a list, but the list will be like much less efficient. We will need like to share the whole list in order to prove someone that you are part of the list, right? So with the Merkle tree, you can just share like the path from the leaf to the root. In this case, we have a small Merkle tree, and we can see that the leaf is ID2. And in order to prove that ID2 is part of the tree, we only need to share like some nodes of the tree, like ID1, hash2, and that's it. This is very, very useful when you have to use zero knowledge proofs, when you have to build circuits, because you need less constraints, it is more efficient, and you can generate proof quicker and faster. So we are actually using a specific version of Merkle trees, which is incremental Merkle trees. This is like a way to add members sequentially. It's like a JavaScript array when you use a push method, right? So you add the first member, the second member will have the position of the first one plus 1. It's just sequential. This is very useful when you have to build on-chain Merkle tree implementations, because every time you need to add a new leaf, you don't need to like use all the entire tree. You don't need all the nodes. You just need, also in this case, the path from the leaf to the root. As you can see here, this is a Merkle tree, so yeah, we need to think about bigger Merkle trees. But let's see, if we want to add ID 4, we just need one node in this case, which is hash1, and ID 3, sorry. So we will need to hash ID 4 and ID 3. We will need to update hash2. Then we will need to hash hash2, the new hash2 and hash1. And we will need to update the root. As you can see, we have not used ID1, ID2, but in a like bigger Merkle tree, you will realize that we don't need to use many nodes. It's just an amount of nodes which equals the depth of the tree. So yeah, this is very useful on chain because, of course, you don't have to store a lot of data, and storing data on chain is really expensive. So yeah, let's talk about Zk proofs. Once users generate an identity, create an identity, and join a group, they can finally generate a proof to like signal anonymously, to send anonymous messages. There is a JavaScript library for these too. There are two functions you can use. The first one is generate proof. The second one, verify proof. Pretty simple. So actually, you can use the verify proof if you are building an off-chain application. If you're building an on-chain application, you can even use the controls, right? And you can verify a proof on-chain. Generate proof takes 4 parameters. The first one is the identity. The second one is the group that we have seen. And the third one, 42, is what we call external nullifier. The external nullifier, I will talk about it later. It's very important to prevent the same proof from being verified twice. It prevents like double spending and double voting, for example. The fourth parameter is hello world. In this case, it's a text message, and it's the signal. As I said before, it can be a string, a text message, but it can even be a number. It can be everything. It can be an hash, so you can hash like the data you want, and just use the hash as a signal. So, of course, the zero-knowledge proofs work because there is a circuit. So the Semaphore circuit is very like small. We can split it into 3 different parts. The first part is about Merkle trees. So once you have your identity, your secret values, like trapdoor and nullifier, you can pass those values to the generate proof function, right? Your identity. Within the circuits, inside the circuits, those values are hashed, and their hash is the secret. The hash of the secret is the identity commitment, as I explained before. The identity commitment is basically the leaf of the tree. So there is like a Merkle tree verifier that takes that leaf and the Merkle proof, which in this case is the siblings node plus path indices. And basically the output of this verification is the new Merkle root. So yeah, it calculates the hashes from the leaf to the root, and then we have like a root as an output. And we usually have a public Merkle tree somewhere, so we can check if the output of this circuit, the output of the Merkle proof of a user, matches the public Merkle tree. And if they match, it means the proof is valid, basically. This is how our contracts work. The second part of the circuit is about nullifiers. So we have the identity nullifier, which is private. We have the external nullifier, which can be, it's like the topic of the application we are building. So if we are building a voting app, the external nullifier can be the poll ID or the ballot ID. And the nullifier and the output of this circuit is the hash of these 2 values, and it's public. in our contracts, we are saving the nullifier hashes. So let's make an example here. If we are building a voting app, and if the identity nullifier is 1, and the external nullifier is the ID of the poll, like let's say 2, and the nullifier hash is free, of course it's not free, but just to make an example, the first time a user sends, creates a proof and sends it to the contract, we save the nullifier hash, which is 3. The second time the same user, the same voter creates another proof, they will need to use the same values, right? The same input values, because the identity is the same. So the identity nullifier is still 1. The external nullifier is a public value and is still 2. If they use a different value, everyone can see that that value is different because it's a public value. And their hash is still the same, of course, because the pre-image is the same. So the nullifier hash will be free, still free. And the contract can check if that value is the same as before. And if it's the same as before, we can just not accept that vote, right? So yeah, this is just an example, but it works in this way. The third part of the circuits are about signals. This is like the most simple part, probably. A signal can be, as I said before, everything, whatever you want. But in the end, it is a number, a big number. And in this case, we need an additional constraint here. We call that, actually people in general call it dummy square. And this constraint is needed because it prevents the same proof from being reused with different signals. This is quite technical, but there is a nice article from the geometry team which explains this in deep. So I can provide that link later if you want. And yeah, this is the last part of the circuit. So now I would like to show you an example of architecture of a DApp built on top of Semaphore. As you can see, the components are the same as a normal DApp. So there is the blockchain, and there is the web app, and there is a front end and a back end, right? Sometimes there is no back end in a DApp, but we need it here. So let's start from the front end. We have a set of JavaScript libraries, identity, group, and proof. We need those libraries to generate a proof. And the Semaphore protocol data library is needed because we need to fetch data from the contracts, right? Using the contract logs. So what data? We need the members, for example. If we have an on-chain contract with a list of members, we need to fetch those members, right? Because as I said before, you may use an on-chain Merkle tree. So that library is usually used to fetch members, and then to create a group, and then to generate a proof. But once the user generates a proof, they can't send that proof to the contract directly because the proof will be connected with the Ethereum address. So we need to break that connection. And in order to break it, there are many solutions, but one solution is to have a relier in the backend. And the relier can just send the sticky proof to the server, sorry, to the contracts. And in this way, the Ethereum address is the backend one. So there is no connection between the user's Ethereum address and ZK proof. This is one way. There are other ways, like account abstraction. There are some experimental applications in our repository that you can check. But probably there will be other ways too. It will be nice to use only a front end and contracts without backend, at least for simple applications. So yeah, actually, I would like to show you our demo, if I can here. Okay, this is our boilerplate, our Semaphore boilerplate you can use to build your own application. If you go to GitHub, you can see that this is also a template. You can just use this template to build your application. And it's pretty much like the architecture I showed you before. This is the web app you can use. You can generate a random identity. I don't know if you see the link. It's demo.semaphore.pse.dev. You can generate random identities here. The next step is joining a group. There is only one group here. Let's hope that it works. It needs some time because even when we join a group, the relayer is sending the transaction to join the group. So we need to wait for the transaction. Okay. Yeah, once we are a member of this group, we can generate anonymous feedback. I can't see the screen here, but yeah, I will try to. Okay. And in this case, like I said before, we are sending the zero knowledge proof to the server. There is a relayer. The relayer of our boilerplate is the Open Zeppelin relayer, so you can use that, of course. I think there are other solutions too. Okay, it worked. I think you can try it. Yeah. So, okay. So what I would like to do now is to talk about Semaphore before and like collect feedback if you have any idea or everything. So Semaphore before, first of all, thanks to the community feedback, we have found some weaknesses in the protocol. And based on those weaknesses, we have tried to make it better, make Semaphore in general better. The main weaknesses we have found, or the community has found, are expensive on-chain tree insertions. This is very critical because it's important to make it even more cheaper. And yeah, I will show you like what we have done later. But every time you add a new leaf now, with the current Merkle tree, it costs something like 1 million unit of gas, which is too much. Also when you update or remove a member. So the other weakness, two identity secrets rather than one. This is like the most common questions people ask us, because they ask why there are like two identity secrets, the trapdoor and the nullifier with those weird names. And yeah, we actually can use one value, I think, and with Semaphore before we have one value only. It's pretty simple, more simple than before for sure. Another weakness is no signature, which means that you can't use your like private key or in Semaphore v3 your two secret values to sign messages, right? It's just a random value basically, or two random values. And it's not like a ECDSA or EDDSA. So we have thought about it and we are considering using EDDSA. Another important aspect or weakness is the dimension of our packages, which is very critical when people can't use 4G connections or 5G connections. If we try to download like the main page of a website built on top of Semaphore with a 3G connection, that will take a lot of time. So we need to work on that definitely, because not all people in the world can like use 4G connection. So I would split the Semaphore before changes into two parts. The first part is about circuits. We changed the variable names from external nullifier to scope. We would like to receive feedback here too, because we thought it was more like clearer. And because a lot of people ask us what's the difference between external nullifier and nullifier hash? And the external nullifier is more like a topic or a scope actually, so that should be more clear. Another change we have made is about the identity. As I said before, we have one identity rather than two now, and we are considering using EDDSA rather than Poseidon hashes. And we have also tried to improve our secrets in general by using new circum features like anonymous components. And as you can see, the number of lines of code is much less with the new circuits. It's 33 for the Merkle tree and 23 3 for the Semaphore circuit. So the old one was, the current one actually is 19 for Semaphore and 40 for Merkle tree. So it's much simpler and neater now. And this is very important because people, developers mainly, should be able to see the code and to understand how it works. So the second part is about data structure. This is very, very important because it has allowed us to make insertions cheaper. So we are not using zero hashes anymore. So in the current implementation, when a parent node has one child, we are using a second value to hash the child nodes, and we call that value zero hash. Basically, with Semaphore v4, with the new data structure, we are not using that zero hash anymore. We are just the like value of the parent node, if there is only one child, is the same as the child node. So this allows us to save a lot of hashes. We need to hash less values in general. The second important change is about the depth of the tree. We have a dynamic depth now, so the number of leaves, for example, if we have a tree with 1,000 members, 1,000 leaves, in the current implementation, there is a static depth, and you are forced to use the like 16, which is the minor one. But with the new tree, if there are 1,000 members, you can just have a dynamic depth, which should be 10. So if the tree depth is 10, the distance between the leaf and the root is shorter. The path is shorter, so you need to use less hashes every time you add a new leaf and every time you prove that you are part of that Merkle tree, because the Merkle proof is like the path between the leaf and the root. We also have another function which has been very useful for Zupas 2, which is batch insertion function, and that function allows us to like add many members at once in a more efficient way rather than inserting members one by one. Yeah, if you want to check our changes, you can go to the GitHub repository in our Semaphore organization. It's called Research. So if you go there, you can see like a list of improvements. You can try the code and you can give us like feedback. We would like to receive a lot of feedback to make this like improvement more a community improvement and to like, yeah, to make Semaphore a better protocol in general. So yeah, this is everything. I think, yeah, it's over. This is like a QR code you can use to go to the Discord, to the Discord of PSC, where there is a channel for Semaphore specifically, where you can ask any questions. Cedoor is my username, so you can find me on Telegram and in Discord too, as I said before. And yeah, so have you any questions?
Can you explain the modifier part in the beginning?
Sure, yeah. This one?
Yeah. Why do you use the identity modifier?
Because you need to connect your private value. I mean, you have to use your private identities, right, somehow, because your proof is personal. So in a voting app, I need to understand if you are the same voters as the previous one, but the vote is anonymous. So I need a way to connect your identity to the nullifier somehow. So yeah.
Identity nullifier is provided by the user? Or?
Yes, the identity nullifier is one of the secret values of your Semaphore identity.
It's kind of random value, right?
Yes, it can be a random value. It depends on the way you create your identities, yeah.
So this is, as far as I understand, for preventing me to double signaling, right?
Yes, exactly, or double voting, if we think about a voting app. We need to know that the second proof with the same the same nullifier hash is yours. So we need to connect that proof to you somehow, but it's anonymous, so we need to make it private, to do it privately. And yeah, indeed, that value is private.
So is there a way to prevent me from double voting for same vote, let's say, election?
Yeah, there is.
I mean,
Yeah.
if the identity is somehow provided by me, I can change my, let's say, private and the identity nullifier to anything and signal it again.
Okay,
I
got
can
it.
get.
You had to join a group before. So let's say the group has some attributes you have to join. I mean, in order to join that group, you have to have specific attributes. For example, let's say you have to be older than 18. So you can't just change your identity. Once you join that group with your identity and you prove that you are older than 18, you can just use that identity, right? Because if you are not part of the group, you can't create the proof.
So I didn't get that part actually. I mean, somehow group or the verifier has to verify me that with using my private identity without the identity nullifier, right? To understand that I'm voting twice.
Okay, you need to use the identity nullifier always though, right?
Yeah.
Okay.
And apart from the identity nullifier, I mean, if we have only the private identity and the group knows me by the private identity and the identity nullifier, right?
Yeah.
So how the group understand me through a random value and my private identity?
I don't think I get it. Can you repeat it?
So you hash the private key of mine, right?
Yeah.
So I create let's
that private key is yours, so it's private.
Key and a random value that provided by me. Actually, so every time I create a new private key for myself, right?
Yeah.
So signal. So group, how group differentiate the identity actually?
So you create your identity only once. You don't create your identity every time you generate a proof. Okay. So
can you go to circuit part? Yeah. No.
This one?
Yeah. So the secret is hashed and it's again hashed.
Yeah.
So it's then there is the identity commitment to the group, right?
Yeah.
So actually I didn't get this part. The private part is actually provided by me, and the identity nullifier, the trapdoor, is actually provided by me, right?
Yes. Yeah.
So I can change the identity nullifier, but keep the private part and generate new hash, new secret, and somehow vote to the same thing again.
You can't change your identity nullifier.
Why? So it's okay.
You wouldn't be in that group, right?
Yes, exactly.
If you change your identity nullifier, you'd have to rejoin the group.
Exactly, yeah.
Okay, it's a constant value then every time I join the group, right?
Yes, once you join the group, you have that identity and you can't change it anymore. In order to use another identity, you have to join the group again with that identity.
Okay, so
right. Yeah.
Why do we hash second time, by the way?
This is, okay, that was V2, and we have done it to make it compatible with other PSE protocols like RLAN, because we were trying to make to create a set of zero knowledge protocols, but in a way that they can be used together. So RLAN needed this secret value here. So we have built Semaphore with that in mind. But actually, I think from an engineering point of view, it's not right.
As far as I understand, you have to keep the second Poseidon hash, but you can get rid of the first hash, right? You can aggregate the data somehow.
Yeah.
So that could be efficient, I think.
Maybe. Yes, sure. Yeah. We don't have that value anymore in Semaphore before.
Okay.
So can you repeat why do we have two hashes?
Sorry?
Why do you have 2 hashes?
2 hashes? Because Semaphore v2 was built with RLAN in mind. Where in PSE there are many protocols. Another protocol is RLAN. Yeah. And RLAN needs this value, this secret value. So we have built Semaphore with that in mind to make them compatible, right? But actually now Ireland don't need it, and I feel like it's more right to build our protocols independently and then think about making them compatible, right? We have many zero knowledge protocols in PSC like Messi, Semaphore, and Aralan. So another challenge is like to provide people many protocols that can be used together, but of course they should also independent and they should be like used separately too.
Yeah. So one way, so you mentioned that in V4 you'll have just single identity. Yeah, you'll have one private key. So one way I think that could be done is just use the secret message as your private key and build a wrapper around it so that that private key gives you identity commitment and a trapdoor. So is that how you do it, or is there something else that
I
you
can show you the circuit actually. I can't see it. Yeah. Semaphore before. Okay. Yeah, these are two options. The first one is just, it uses Poseidon hashes. Yeah, sure. I can't do it from here. Okay, yeah. Can you see it? No problem. So yeah, as you can see here, there is a secret, one secret. I think it's like you were explaining before. And then we hash that value with Poseidon, and that's it. The identity commitment is the hash of the secret. There are no other secrets. And this is one solution. Another one is using EDDSA.
So you got rid of trapdoor. So like what's the like how does the security remain the same?
What? Sorry.
So you got rid of the trapdoor, right? Identity trapdoor.
Yeah.
So like what? So the role that trapdoor was playing earlier. So how's that fulfilled here?
We are not okay.
Yeah. Yeah. Even yeah. If it's generated. Yeah. How is it generated?
Yeah. Thank you.
So what was the? Could you explain the reasoning of like why you originally created a trapdoor and a nullifier?
I can't because I was not there. I'm not sure. Yeah.
So with this new version, you
I think
basically realized like, hey, we actually don't need both. We can just have
exactly.
private value.
Yeah. 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 You should talk with Andrea for each. I think I don't remember the name, but yeah, he built the circuits for Semaphore V2. I think their main reason was for security. It was like an additional security layer, but we actually don't need because it's already quite secure. Yeah.
Yeah. Yeah. So in protocol, so the white paper that's there online of V1, in that there was also a public. Let me.
Yeah.
So in the identity commitment, when you generate identity commitment, there was also a public key that was involved. So there were three things that you used to generate identity commitment.
Yeah.
So like, yeah, what was that about?
It was much more complex. Yeah.
Yeah, so yeah, I could only.
yeah, this,
Yeah.
Do you mind explaining, you mentioned signals, like, is submitting a single signal just signing a message with your Ethereum account? Is it an on-chain transaction? Could it be either, depending on how you're implementing, like, the signal submission, or like, yeah, recording those signals?
You mean like signals, the text
Yeah, so
anonymous
if you,
feeding?
like, my basic understanding is you can generate an identity, you can prove your membership of a group to join a group, and then once you're in a group, you can submit single signals, which might be like feedback or a vote. Like, what is a signal?
Yeah. A signal is just a big number, basically. So it can be an hash, it can be a text message converted to integer. It's just a number. It can be everything you want. It's data you, as a user, wants to send anonymously. And yeah, it's connected to the proof only because it's in the same circuit. Actually, there are no connections with the other pieces of the circuit. And the way you use signal depends on your application. So if it's a voting system, you will need to collect signals on chain, right? Like Ethereum logs. But that depends on your use case. I don't know if you...
Got you. So yeah, depends on how you want to implement it, basically.
Yeah,
like,
exactly.
You could just be signing messages to submit signals and not actually putting transactions on chain.
Of course, yeah. Semaphore is quite general purpose, so you can use it on chain, off chain. You can use it in many ways. Yeah, it's pretty general.
Do you explain the three parts of the group form?
Okay. Yeah. This one?
Yeah, they all is called the one group, right?
Yes.
So there is a group, and the leaves are the members of the group.
Yeah. One Merkle tree is one group.
Did you ever think about the different implementation, maybe not using a Merkle tree instead of Merkle tree, maybe?
Yeah.
Maybe could you use like multi-part computation here, kind of? Could it be, or aggregated proof in the like is in the ZK Snark? I don't know.
Yeah, we have considered other options, and probably we will use something different for Semaphore v5. But the Merkle tree looks like the best solution now for Semaphore v4 because we wanted to keep it like a little bit closer to the actual current implementation we have now. But yeah, there are other solutions. I think I'm not able to talk about that technically now because I don't know how we can use them technically with Semaphore. But yeah, there are other solutions.
So, and in the next version of the Merkle tree, I think you don't hash the zero values, right? So you ignore them. So the hash is actually keep the same. So you get rid of that overhead. That's why you speed up the process.
We need to hash less values, basically. Yeah. So in both cases, not zero hashes means that every time a parent node has a child, it just...
So you can skip the...
Yes, you skip it, basically. You are just assigning the same value as the child to the parent node.
So what is your suggestion to use multi-party computation instead of the Merkle tree?
So instead of hashing like leaf to root every time, maybe you can compute one signature for whole group with the multi-part combination. I think the theory is okay, right?
So instead of you say Merkle tree,
yeah, you can probably
you can do aggregation for each of them and just get them to. I think like it can be very expensive. I don't know. Maybe like they need to.
As far as I see, you use the max depth somewhere in the code, so you could like use hybrid implementation over one, like maybe you can use aggregate proof as well in the like
You mean
root of tree.
you mean two options?
So you can skip somehow, I mean, try to skip the hashing of the root, the leaf chart, right?
Okay.
So maybe you can use aggregate proof of the leaf.
Ah, right. Yeah, that can be, yeah, that can be an option. I think so.
What?
Yeah, proof aggregation.
Yeah.
In the end, we want to keep it simple and where people can
But
use it
you can't keep it simple because it's as far as I understand, it's heart of the system, right? So you have to make it. I mean, most of the gas is used in that part, hashing part, right?
Yes.
So you have to keep it somehow complex but smart.
Yeah, there is a trade-off, I guess.
Yeah.
I think there are trade-offs everywhere. We have to decide.
Yeah, there are other questions? Oh.
So when you say no zero hashes, so this means that so you have tweaked the Merkle whatever the algorithm is to have an if else that if it's zero then we'll have this, otherwise the hashing works as. So you don't come up with some other hashing algorithm where if you append some zero to it, the hash remains the same. It's not that, right? It's just an if else condition.
Yes, it is. Yeah.
And when you do batch insertions, so let's say you have a Merkle tree of 2 to the power 16 nodes. So let's say you insert 100 in one batch, 100 commitments. So do you generate 100 roots, or do you generate just one?
One.
One. Okay.
Yeah, that's the difference.
Yeah,
The
so
batch function creates, yes. There are much less hashes because you don't need to update the root every time. And not only the root, but also some nodes between the leaf and the root.
Would that somehow like leak away some information? I'm not so sure about this, but yeah, like this indicate, like let's say like case one, you have flexibility, you can choose any Merkle root and prove that I was existing in this, versus where you have batches. I'm not sure if it can leak away some information, but
I didn't get it.
so it's not a well thought idea. It just came up.
So, now can you explain it?
So if you let's say there were 5 batches. Let's say you start a new group and you add 5 batches of 100, 100, 100.
Okay.
Somehow, rather than having 500 tree roots versus having just 5 tree roots, and you prove using some.
All right. Yes. Yeah. This was a solution actually. We have thought about it. Okay. It's like there is a name too, Merkle forest. Rather than having one Merkle tree, you have many subtrees, right? So you can create one Merkle tree by adding like 100 nodes, another one by adding other like 100 nodes. And you can have many Merkle trees, and when you have to prove that you are part of one of those Merkle trees, you can just use the root of that specific Merkle tree, right? Do you mean that?
Not exactly.
Okay.
I think I'll have to think more about it.
Okay. Yeah. We can talk about it later, maybe.
Have you guys thought about like using probably Merkle trees to like shorten the inclusion proof?
Yes, yeah. That also was something that like it would make the protocol more complex. So we have tried to keep it simple. So it can be a nice feature for some specific use cases, but the main goal for Semaphore is to keep it simple and to try to coverage as many use cases as possible. So yeah.
Thank you.
No worries. Mm-hmm.
Yeah, could you maybe talk through potential I'm trying to get a hand on like the relayer implementation.
Yeah.
Like I was just looking at the boilerplate, and I think that looks like you just have a backend that relays the or like sends the transaction for the user.
Yeah.
So are there like services you would use or recommend, or like implementations you've seen of Semaphore of like using some, I don't know, decentralized relayer to forward the messages?
There is the Open Zeppelin relayer, and we are
Okay.
using it with this boilerplate. There are other solutions. There is Gelato, I think, but there are probably other relayers too. And as I said before, besides relayers, you can even use other solutions like account abstraction. Yeah, it's quite experimental. So yeah,
Thanks.
no problem. Okay.
Yeah. So rather than, so now that you have generated a ZK proof, and so what's the security flaw in this, that you just generate a random new account and just submit a proof, and so your proof won't leak away your identity, right? Just the proof. So
Yeah.
so the relayer is just to ensure that your secret. Okay, sorry, I got it.
Okay.
Sorry.
Yeah, the relayer doesn't know anything about your secrets, so it's just an encrypted proof.
So the identity leakage might be from the IP that.
That's true. Yeah.
Yeah. So that's
Of
that's
course,
what you're solving
it
there.
cannot be fully anonymous, right? So you need to use other technologies, I guess, to hide your IP other than Semaphore.
There is no subgroups, right?
The concept of subgroups is something we have thought about. Yeah, like subtrees. Yes, it's something, I think Macy has something like that, right? Subtrees within the circuits. But yeah, with Semaphore, again, we are trying to keep it simple. Maybe another similar concept is like you are part of the group A, you want to, there is another group B, and you want to join the group B only if you are part of the group A. So this is kind of a subgroup in a sense. And this can be done with the current version of Semaphore.
Yeah, pretty sure you can do that.
Yeah.
But having a subgroup maybe actually simplify your implementation probably.
Probably, yeah. Well, yeah, it will be great to receive feedback for that too. Are there other questions? Okay. So